Thank you for the introduction. So hi, my name is David. I work in Florian's group. Florian did get sick, unfortunately. I'm here to replace him. Fully recognizing that's going to be impossible probably, but I'll do the best I can. Other main contributors to our presentation today is Srini Dalby. She did most of the runs and the post-processing for the case. Katja's working on modeling aspects, Andreas working on meshing, and obviously Florian is leading all that effort. I'll dive right into it. I have a lot of slides, a lot of ground to cover. I did stick in the presentation to the results that we are all familiar with, and so I will go rather quickly across the results section and rely on you having done questions if there is anything unclear. So we did run all of that in our GPU solver. Don't know if it's still appropriate to call it new. It's been now out there for a couple of years. I've been involved in developing this from very much the beginning. It is fully GPU native, meaning we don't transfer data on the solver side in between the GPU and the CPU. I think speed is very relevant for all of this. We see that there's still a lot of spread in the data, and I think it's still looking to me as if it's still a bit of an art to get a good prediction here, and having the possibility to run different configurations depends on how fast the solver is. Our solver approximately has a speed up of 1200 CPUs being replaced by one NVIDIA A100 GPU. I will give you a bit more details on the next slide about that. As said, all solver operations are on the GPU. There's no data transfer, and we do not try to just repeat everything that we did on the CPU, but just taking the opportunity to develop a new solver, work on robustness and speed and accuracy while doing so. The clocking for this very case in LES, our own mesh, the smaller one, has 277 million cells, and per iteration we use 2 iterations per time step. Simple C, 0.185 seconds per iteration, 0.37 seconds per time step. So one CDU comes down to 0.8 hours. For SBES, per iteration time is a bit slow because we have to solve more equations. So it's 0.316 seconds, and we get a 1.3 hours per flow over time. We use probably a smaller time step than most of what I've seen so far here. It's just such that we have CFL smaller 2 in the relevant areas of the flow, and we believe that that is a good approach. At least it takes out some uncertainty. That's what I promised. So this is our official performance slide. It's done actually on a very similar case, 250 million cells. And so we are basically somewhere here, 32 L40s, 0.09. This one did 5 iterations, so that's a bit faster than per iteration and had no post-processing. The solve is pretty well verified by now. Obviously, we can do HIT, we can do channel flows. Channel flows are particularly interesting, I think, for wall model LES. You can see we use the second point as an input to the wall function, so we can, we don't have a log layer mismatch anymore, and the resolution is independent of the Reynolds number. I mean, the other way around, we can use the same resolution independent of the Reynolds number for channel flow and for general boundary layers. So keep that in mind. I think it's going to be somehow more important later. We also participate in the wall model LES workshop, and I think also there for separated turbulent flows, we have pretty convincing results at the moment. The LES runs use a purely central formulation in the vector quantities, and we use, as said, the second point as an input to the wall function. We use the whale model current point, constant 0.65. For SBES runs, we do use some approximately fourth order reconstruction, and we introduce some Wiener type smoothings, while the phase variance are kept central. Some words on meshing. Those meshes that I'll present first are based on the meshes you already saw in the AutoCFD4 workshop. All meshes that are created by ourselves are using rapid octave meshing. The meshing time, that's also interesting, on 320 cores is between 10 for the smaller and 31 minutes for the larger meshes. Now, those meshes, they look sort of like, let's say like this. This is the workshop mesh for a reference. This is the rapid octave mesh. It's called 1.2. It's got closed grooves. It's one thing to keep in mind here. On the tires, this is the MS1 wall function LES, and this one is basically a systematic, or if you want, naive refinement approach, just basically double resolution on all surfaces while keeping most of the volume boxes constant size. That's detailing it a little bit. I won't go into much detail. We have a refinement box here. We have a refinement box around the lip and here in the beginning of the windshield. And also we try to keep close to the workshop mesh in the wake refinements. Overall, the wall function LES has 277 cell count, million cell count for case 2A, and then the naive refinement has almost 700 million. The SBES mesh 380 million, and compared to the workshop mesh, of course, a lot finer. Maybe interesting is the minimum size, or actually the maximum size on the model, which is 4 millimeters for LES, and then the refined one 2 millimeters, 4 millimeters for the SBES mesh, but then 8 prism layers, and they have a stretching. So we get down to roughly y+1, a bit more, and a lot finer than the workshop mesh actually. Okay, wall function LES comparison. We do not get, we're not entirely happy with the results we have, but that's what we did get so far. 0.27 for drag. I think that's the most relevant quantity. The mesh refinement did not actually make a big difference here. Actually, no difference at all. And I think that is just because the boundary layers are already captured by the coarse mesh, and the refinements didn't go into the region where they should be. So the delta CD is, I think, where we are in reasonable agreement. The averaging times we used are a bit short. Probably we did 2 seconds overall run and 1 second of averaging. So as you can see, the spread I think is fairly large. So I don't know about those delta values, 30 digits, how accurate they are. And again, I think I'll just race through those because really the message here is that mesh refinement for wall function LES, it didn't make any difference, and it's just basically on every slide. Those are the CF values. There you can see a little bit of a difference. Underbody center line, basically no difference. Those are very hard to see probably, but there is very little difference in the velocity profiles. We do not capture very well that wake. We had a bit of an issue with post-processing. We were always thinking we get the wake better because we plotted those experiments onto V4, and then it did match better. But so now we know we have something to work on there. And then I think those just reflecting that we did in these LES runs not really capture the rear window separation. Also seen from the CP profiles, and again, the mesh refinement didn't change that much. But then same story for the A pillar. Not much of a change with mesh refinement, although I would say the local data for any of our CP values is not bad. Now for the side window, and particularly behind the side mirror, we did see an improvement. So this 208 point is the one right behind that mirror by the mesh refinement, and that is probably the major difference actually between the two runs we want to say. This is the superior end. I think this is where a lot of the drag difference is probably coming from, because the wake's not well captured. And again, not much happening with this type of approach for mesh refinement. Same story for underbody off center line. And then let's go to the SBES comparison. The SBES, we did actually with the workshop mesh get a bit of a better agreement in overall drag prediction, while it was the coarser mesh. And so the overall drag for the AutoCFD workshop mesh, we got 0.271, and the our own Octree rapid Octree mesh 0.282. And again, I think the deltas in both cases are reasonably well predicted. Now, cumulative drag, see probably the main difference in drag starting somewhere here in front of the wheel, which might make sense because our mesh did not have those grooves on the tires. That is something we have to look into, certainly. The CF, fairly well agreeing. The underbody centerline velocity, I think we like get spot on with our refined mesh. Also, actually, for those velocities, there is hardly anything, you can spot where to improve those velocity results for the finer mesh. Then again, here, that wake's not very well captured, something to work on. And also that trunk separation on the fine mesh is captured pretty well. Same story for the CP plots, actually. The finer mesh gets like pretty much everything pretty nicely. And then we're working on transferring some of the findings from the SBES run, because the SBES run used an angular refinement criterion. So we use an angular refinement criterion now for the LES runs as well. It does actually use more of a refinement compared to the SBES, because we don't have prism layers in that case. And this is the sort of mesh that we then are using and evaluating. It's a bit coarser, actually, overall. It's 4 millimeters on the body. But the refinement toward the curvature regions is a lot better. And so the results also did actually improve. This mesh also has the grooves on the tires, anyway, by the way. So we see a good reduction in drag, going from 7% mismatch to 3.5% mismatch. The difference in cumulative drag is mainly actually coming from a better prediction up here, where we had the angular refinement and then we lose some, and we did have here an over prediction now of the separation. In fact, we do capture with that mesh. We do capture a bit better here the wake coming from the underbody, I will say, which I think is interesting. And then, as I said, here we had a coarsening on the rear window, 4 millimeter to 2 millimeter in comparison, and we now do see a bit of an over prediction of the separation instead of the under prediction. But then here at the onset, where we had the angular refinement added, we do capture the flow a lot better. Now, for all the other CP plots on the pillars, where we had a lot of refinement added by this mesh, we do see a systematic improvement, basically, wherever the refinement was. We did also cut some of the wake boxes, like behind the mirror, and you can see, there's some of the velocity profiles did get worse because of that. Rear end pretty much unchanged. Same story on the side, and also basically in the underbody region. So to summarize, we believe that GPU is an enabling technology for wall function LES, because in the end, you need to have a really fast solver for those expensive simulations. All simulations are very close to local data, local experimental data. the velocity, both in velocity and pressure coefficients. The only systematic difference that we do see in all simulations, and again, we've only learned about that recently, is in the vague V5 velocity profile. All simulations are high on CD relative to the experimental data, something to work on. Drag differences between case 2A and 2B are reasonably accurate, I would think. And then the wall function LES did not improve by that, systematic refinement, but now we're working on another mesh and we can see some systematic improvements where we would expect them, and we hope to have better results soon. We submitted a SAE paper abstract and have a following up paper still working on that case. The SBES is closer. For all Ansys, the mesh results are closer compared to local experimental data compared to the provided workshop mesh. However, the overall CD predictions worse. So that's something to keep working on, and well, probably this workshop chose the right location in Riddle Hall here. Thank you for the invitation, and I'm ready to take some questions.